In this video, I'm going to give a brief summary of the topics and materials that will be covered in this PDE course. I'll be explaining what prerequisites you need to have to be able to successfully complete this course. And at the end of the video, I'll show you some of the PDEs that you will learn to solve by the end of this course. So let's get started. In order to get to partial differential equations from basics, we still need to have some minimal mathematical background. For example, we need to be familiar with the concepts of function, derivative, and integral. In particular, you need to know what a single variable function is, what a multivariable function is, and how you can take derivative and integral of these functions. For example, you need to know what df dx is and how you can calculate that, how you can calculate the higher order derivatives of a function. And in the context of multivariable functions, for example, you need to be familiar with the partial derivatives concept, partial f, partial x, partial f, partial y, for example, etc., and how you can calculate these stuffs. You need to also know how to calculate the integral of a function like fx, so integral fx dx. So you need to know how to calculate this term, and similarly you need to know how to calculate multiple integrals. So for example, double integral of fx and y dx dy. So how you can calculate that. So if you are familiar with these concepts, then you should be able to comfortably follow the rest of this course. Otherwise, I definitely recommend you to use other resources to familiarize yourself with these concepts, and then come back to the rest of this course. So we're going to start with some basic concepts. We're going to talk about vectors and inner product of two vectors like A and B, and then we get to the orthogonal vectors, and we're going to show that two vectors are orthogonal when their inner product is 0, basically. And we're going to extend this concept to functions, and we introduce the concept of inner product for functions, and by analogy we call two functions to be orthogonal when their inner product is 0. And from that we introduce a very important concept, orthogonal series expansion. And basically that means if you have a set of orthogonal functions like phi naught, phi 1, phi 2, etc., then this is going to be a very powerful tool. And the reason for that is that it allows you to represent a given function like g as a linear combination of these members, these orthogonal functions. So for example, I can write g as c naught phi naught plus c1 phi 1, and so on. And our job is just to specify these unknown coefficients, c0, c1, c2, etc. And it turns out that Fourier series is then just one specific example of these orthogonal series expansions, wherein we use sine cosine functions. When we get to this point, when we cover all these materials, then we still need to talk about ordinary differential equations, because there is no assumption that you know ordinary differential equations. So we need to cover that, and ODE itself is a kind of very broad topic, so we're not going to go into details of ODE, but at least we're trying to cover all those materials that are needed to enable you to solve partial differential equations. So we're going to talk about those important classes of ODEs, for example, something like second order ODE, something like this, how to solve this equation, and because that's very important. In order to solve a partial differential equation, you need to know these kind of basic concepts. But if you don't know ODE, don't worry, we're going to cover ODE to the extent that is needed for being able to solve partial differential equations. And finally, we get to this important phase of this course, which is solving partial differential equations. And we will talk about two-dimensional, three-dimensional boundary value problems and initial value problems. And some of the examples will include heat equation, wave equation, Laplaces equation, and Poissons equations. And we will talk about some analytical techniques, mainly the separation of variables technique, to solve these equations. And the very unique feature of these techniques is that it allows you to find the solution as a closed form, which means, for example, y can be written as a function of, let's say, x and t. If your function y is dependent on just two variables, x and t, then you can have a bunch of expressions on the right hand side, and from which you can find y at any given, for example, location and time, right? But it's not always possible to use these analytical techniques to find these closed form solutions, and that's where you can resort to other techniques, particularly the numerical techniques, and you can find the numerical solutions. For example, you can use a technique called finite difference method, and this is what we will talk about at the end of this course, and you're going to see that you can solve relatively complex problems using this technique, particularly in situations that you are not able to use the analytical techniques, and that's going to be very powerful. So with that, this is the end of this overview. In the next section, I'm going to show you some of the partial differential equations as a demo, just to help you get some feeling what kind of problems you will be able to solve at the end of this course, and hopefully that gives you a better insight if this course is something that you really want to continue to participate in. Before talking about the partial differential equations that you will learn how to solve in this course, I would like to emphasize two really important points here. Number one is that one single PDE may be describing several problems. For example, the diffusion equation can describe the diffusion of heat, the diffusion of mass, and diffusion of momentum. So once you learn how to solve the diffusion equation, you should be able to apply those skills to solve the diffusion of heat problem, diffusion of mass problem, diffusion of momentum problem, etc. So it's really powerful. And number two, you may ask where the partial differential equation comes from in the first place. For example, how can you derive the diffusion equation? And so the answer is that for most of the problems that we are dealing with, there is an underlying physics that describes how the system behaves. And our job is to write that in the language of mathematics, and that's the modeling part, in which we usually make assumptions and simplifications, and at the end we end up with some governing equations which usually show up as ordinary differential equations or partial differential equations. And in this course I'll try to briefly also talk about the modeling and the underlying physics of a given PDE as much as we can, and that hopefully can give you a deeper insight into the underlying physics of the problem, and hopefully after you solve the partial differential equation, it allows you to be able to analyze those results and say, hey, I know now that this system behaves in this specific way, and that's going to hopefully lead to a deeper understanding of the physics. One of the PDEs that we will discuss in more detail later is the one-dimensional transient heat equation. Let's say we have a rod which is initially at 100 degrees C, and we bring both of its ends in contact with another material which is always at 0 degrees C. So our goal is to find the temperature variation within the rod over time. So temperature then is going to be a function of space and time. And x here is just the distance from one end of the rod. So when we study such a problem, we try to model the system and we make some assumptions. For this specific case, for example, we assume that the thermal diffusivity of the system is constant. And thermal diffusivity is just a property of the material that shows how fast heat can diffuse within that material. And this property is generally a function of temperature. But for simplicity, we just make this assumption that this property remains constant. And the other assumption here is that there is no heat convection. And we know that around this rod we can have another material, another gas, probably like air, but we just neglect the heat transfer from rod to the air. That's another assumption that we make here to make our problem simpler. And we make some other assumptions here, and at the end we end up with this partial differential equation shown here, and this is the PDE that we have, and here we have the initial condition which basically says that at time equals 0 temperature is at 100 degrees C, and we have two boundary conditions for both ends of the rod, and basically it says that the temperature is 0 at both of these ends of the rod. And if we solve this partial differential equation for any given material, then we can find the solution and we can plot that, and we can find the how the temperature profile will look like inside that material, inside that rod at any given time. So for example, for glass with this specific thermal diffusivity, we have plotted the temperature profile at different times, and you can see how it looks like here. So for example, at 20 seconds you can see that the temperature profile is still very close to initial temperature, which means for the majority of the rod the temperature remains at 100 degrees C, but very close to the boundary you can see that the temperature drops to 0. As time goes by, then the effects of boundary starts to penetrate, starts to diffuse into the system deeper and deeper. But in the case of glass, even after 2000 seconds you can see that this diffusion takes place maybe around 20 centimeter from the boundary, and the majority of the rod does not see the effects of the boundary, and that's because the diffusivity of the glass is very, very small, which means the heat diffuses within the glass very slowly. In the case of the steel, you can see that the cooling down process is faster. You can see that, for example, after 2000 seconds, all this area has already seen the effects of boundary, so the effects of boundary has diffused all the way up to here. But you can see it's still close to the center, the temperature is still at 100 degrees C. That means the effective boundary has not yet reached to this area. And it takes longer time for this portion of the steel, for this steel rod to see the effects of 0 degree C temperature of the boundary. In the case of aluminum, because of having a much larger diffusivity constant, this cooling down process takes place much faster, and you can see that even after 200 seconds the temperature of the center has already decreased to 95 or something like that degrees C. So that means the center of the rod has already seen the effects of the boundary, and as time goes by, for example after 2000 seconds from the beginning of this process, the temperature of the center decreases even below 20 degrees C. And basically this is the way that we at the end we can study and analyze the results, and we can interpret the results. You can see here how the temperature profile varies over time within different materials, glass, steel, and aluminum. And you can see particularly that the heat diffusion within the glass is much slower than that within the steel, and similarly the heat diffusion within steel is much slower than that within the aluminum. One of the other problems that you will learn to solve in this course is the startup of a shear flow. And let me describe this problem first. Let's say we have a liquid film confined between two parallel plates, and the liquid is initially at rest, meaning that its speed is 0 everywhere, and at some point all of a sudden you start moving the upper plate to the right hand side at a given speed like u equals 1, and we want to see how the liquid flows over time, and we want to find its speed basically. So speed then is going to be a function of the location, the space, and time, and y here is just the distance from the lower plate. So this is a problem, and if you do some modeling, making some assumptions and simplifications, you can end up with this partial differential equation, and you can see that this is basically a diffusion equation. And in fact the problem, it turns out, that is just a diffusion of momentum. Why? Because you just apply a change to the momentum of your boundary, and you want to see how this change will penetrate, how it will diffuse into your system over time. So that's why we have a diffusion equation here. And we also have a initial condition, which basically says that at time equals 0, speed is 0 everywhere. And we also have two boundary conditions, one for the lower plate and the other one for the upper plate. And for the lower plate, speed is going to be 0, and for the upper plate, speed is going to be 1, which is the same speed of the plate itself. And these boundary conditions are called no-slip boundary conditions. And what it means basically is that in the context of fluid mechanics is that whenever you have a solid right next to a liquid, what happens is that right at the interface of the solid and liquid, right here, right at the interface, the liquid and solid are going to have the same speed. That's why that, for example, for the lower plate, where we have a stationary plate, we consider the liquid speed to also be 0. But for the upper plate, where the speed of the plate is 1, we then consider the speed of the liquid to be also the same, 1. So now we have the PDE, initial condition, and boundary conditions, and you can solve this problem mathematically and then you can find this solution in a closed form, meaning that u then is going to be a function of y and t. So there is going to be an expression. If you evaluate that expression at any given y and t, then it's going to give you a value for u. But let's look at the briefly look at the underlying physics here. So let's start with the initial condition. So we have zero speed everywhere. Right after you move the upper plate to the right hand side, the very first layer of liquid is going to be moving to the right hand side. And after some time, what will happen is that this layer, because it's moving now, this layer of liquid is going to drag the layer beneath itself to the right hand side. So then you will get something like this. And shortly after that, then each layer of liquid will be dragging the layer right underneath itself to the right hand side. And you can see that over time the effects of this boundary, upper boundary, is going to be diffusing deeper and deeper into your system. So for example, at the beginning you have a very thin layer of liquid right next to the upper plate that sees the effects of the boundary, but the thickness of this layer that sees the effects of boundary is going to be increasing over time. And after a sufficiently long time, what you will get is this type of profile. On the right hand side, we have plotted the results that we have obtained after solving this partial differential equation, and the results have been shown here for various times. And you can see after a sufficiently long time you get this linear profile that I mentioned here. This video here shows you how the velocity profile varies over time, and particularly you can see that at the beginning the speed is 0 everywhere except close to the upper plate where the speed is approaching 1. But as time goes by, you can see that the lower layers of liquid also start moving to the right hand side. Another type of PDE that you will learn to solve in this course is the Laplaces equation. And it turns out that the Laplaces equation can describe the steady state heat conduction problem. And here is the Laplaces equation, and for example, for this specific case we have two insulated boundary conditions, top and bottom, and we have two variable temperature profile imposed on the left and right hand side of this plate, and the goal is to find the temperature distribution within this plate. And after solving this PDE, you would get a contour for temperature as shown here on the right hand side. And you're going to learn how to solve this type of PDE and how you can obtain the results and how you can interpret the obtained results. Another type of PDE that we will discuss in this course is the Poissons equation. And you can see that this equation is similar to the Laplaces equation, with the difference that now we have an additional term here. And this term is usually called the source term because it sometimes takes into account the effects of a source term, for example in the heat problem or in the electric potential problem, because it turns out that this PDE can describe two different problems. One of them is is the electric potential distribution within a material, and the other one is the steady-state temperature distribution within a material. And in the context of the heat equation, we can have a generation of heat, or we can have a dissipation of heat within the material. Let's say, for example, we have a heat generator inside this material, and we apply this type of boundary condition on the left hand side. So u equals 0 here, on the lower side u equals 0, and on the right hand side u equals 1. And these three boundary conditions are listed here. These are the boundary conditions that we specify for this specific example. And then we are trying to adjust the intensity of the source term here, and we want to see how the temperature distribution will be affected by changing the source term. So we expect the temperature to be a function of x and y. Since this is a steady-state problem, we don't have the effects of time here, and we're going to be having a function which is just dependent on two independent variables, x and y. And if we set the source term to be 0, then this equation, this Poissons equation, will be reduced to the Laplaces equation. And if you solve that, then you would get the temperature distribution as shown here. And you can see that on the left hand side, then the temperature is 0, which is satisfying the boundary condition. Similarly, on the lower side you get a 0 temperature, and on the right hand side now you get a temperature of 1, which is represented by this yellowish color here. If you increase the intensity of your source term, then for example to 0.1, then the temperature distribution is going to be slightly changing compared to the case that you don't have any heat source inside your material. And if you increase the source term even further, for example to 1, then what you can see is that a significant change will take place here inside the material. The temperature distribution now is quite different, and particularly you can see that the maximum temperature inside your material can exceed the temperature that you impose on the boundaries. For example, in this case you can see that the maximum temperature can reach to even 1.6, which is larger than the temperature of 1 that you apply on the right hand side. And the reason for that is that you generate some excess of heat inside your material, and that results in a larger value for your temperature inside the material. And at the end, the heat is going to be transferred from inside your material to the outside, from left and right. Compared to the case that you don't have any heat source inside the material, if you compare that, then you see that for that situation you have the heat flux from right hand side to the left hand side, from the higher temperature to the lower temperature. And if you keep increasing the source term to even kind of larger levels, for example s equals 10, then you can see that the maximum temperature within your material can become even larger, and can reach something like 12, which is much larger than the u equals 1 that you impose on the right hand side. The wave equation is another important problem that we will study in this course. Let me describe the problem first. We are having a string which is fastened on its both ends, and we apply an initial displacement to the string, which is described by function fx, and we also give the string an initial speed described by gx. So we let the string go, and we want to see how the string displaces over time. And so this is the physical description of this problem. And on the left hand side you can see the mathematical description for this problem. And as a side note, the magnitude of the tension within the string and also its density are going to be important on how the system behaves, and they show up in the partial differential equation as a constant A, which is just the square root of tension over mass per unit length. Now let's look at a very simple example here. Let's assume A is going to be 1, L is going to be 1, and we have G also equals 0. So that means we just let the string go from the initial position without applying any speed to the string. So it's going to be released from rest. And we also apply this initial displacement to the string, and that's going to be a simple sinusoidal displacement. If I draw that, that's going to look like this. As a function of x, the displacement will look like this. At L equals 1, the string is fastened, and on the x equals 0, the string is fastened too. At the center, you get a displacement equals 0.1. So if you let the string go, then it's going to start displacing vertically upward and downward, and you get a nice standing wave, as you can see here. This video is going to show you how a string vibrates over time with two different initial displacement profiles. On the left hand side, you have a symmetric profile at the beginning, whereas in the right hand side the string has a skewed displacement profile at the beginning. And if we let the string go, you can see that the left hand side is going to show a standing wave, whereas the right hand side results in a traveling wave. The one-dimensional wave equation can be extended to two-dimension in order to study the vibration of an elastic membrane. And if we do that, then we get this partial differential equation shown here, and you can see that now we have this additional term, and because of having now two second order partial derivative with respect to x and y, so now we need to have four boundary conditions. And for this specific example that we're going to study here, we assume that all edges of the membrane are fixed. So all these edges are fixed, and that means that displacement is going to be 0 for those edges, u equals 0. So these are the boundary conditions that we have, and because of the second order partial derivative with respect to time, we need to have two initial conditions, and we use similar conditions that we use for one-dimensional wave equation, meaning that we describe the initial displacement profile using this function f, and also the initial speed of the membrane, which is this function here, g. So after solving this problem for any given functions of f and g, then you would get the solution something like u equals a function of x and y and t. Now the displacement is going to be a function of space, x and y, and time. So for any given location and any given time, then you can evaluate the expression that you have on the right hand side obtained from the from solving the partial differential equation, and that's going to give you the displacement at that given space and time. Now, in order to see how the results will look like, let's look at a very simple example. let's assume that A equals 1 and the membrane is 1 meter long in X and Y direction, and we have G equals 0, which basically means that we just release the membrane from rest and it doesn't have any initial speed. And we consider two different types of initial displacement profile. One of them is symmetric and the other one has a kind of the skew in this direction, in Y direction. This video shows how the membrane vibrates for each of the initial displacement profiles, and you can see that for the symmetric one the vibration is going to be a standing wave, whereas the right hand side shows a traveling wave. And with that, this is the end of this video, and I hope you will find this course useful.